So this is a fall 2019 exam 3, I'm pretty sure. Problem number 3. Now this is the word problem. I can't imagine that we would put this on a shorter test, but at least all the problem-y parts. Hey, Meg. So we have the Grand Coulee Dam. It's one of the largest concrete structures in the world. So these things are going to be huge. These are not going to be like maybe what we've seen in class in terms of what you would see in an automobile or something. These things are going to be ginormous. Okay, look how tall this person is, and look at this system. Okay, so I'm expecting some pretty bigger numbers than what we're used to seeing in terms of shaft design. The Grand Coulee Dam is one of the largest concrete structures in the world. It has 3 power plants that house multiple hydroelectric power turbines. The largest of these turbines produces 165,000 horsepower. That'd be like one massive truck, while spinning at 36 RPM. The turbine generator shaft is made of stainless steel with a yield of 50 KSI and a modulus of rigidity of 11,000 KSI. And we want to determine the outer diameter of the hollow turbine generator shaft to the nearest inch if the wall thickness is 12 inches and the allowed stress is 1/2 of yield. So we are allowed 1/2 of yield. If this is yield, we are allowed half of that. And if we're looking at this ginormous shaft, okay, and I want to design the, it says design the diameter. So I want to design the diameter. Okay, and I'm told that it has a thickness, holy cow, a thickness of 12 inches. So if I'm looking at my inner radius, my radius inner, okay, that radius inner is going to be a radius outer minus 12. So I'm going to have a radius inner of radius outer minus 12, which I don't know what that is. I'm going to have a radius outer. I don't know, or that's what I'm trying to design. Okay, and so I know I'm probably going to have a J, which is pi over 2, radius outer to the 4th. And if I'm looking at shear stress, I have TC over J. So I have that, I have that. Okay, so I'm told horsepower, so I can get to torque from horsepower, and I have an allowable. So the first thing I'm going to do is I have an allowable of 1/2 yield. So I have 1/2 of 50 KSI, and that gives me 25 KSI. And that's going to be the stress that I can use in my design. Okay, and I know that shear stress is TC over J. So I've got 25 KSI equals T. Okay, and then I have C, which is that outer radius, pi over 2. And then I have that radius outer to the 4th minus, this is getting very, very ugly. Okay, radius outer minus 12 to the 4th. And I need to find the radius and the torque. Now I need to do some unit conversions. So I know that power is 2 pi frequency times that torque, and I know that we were given horsepower, and we don't really work well with horsepower. I'm going to go ahead and rewrite this equation in terms of torque, and I'm going to get power over 2 pi frequency. Okay, frequency. And again, we're going to want that like in radians, because that's what we work with. With torque is radians. We don't work with revolutions, and we don't work with degrees. So anyways, bear with me. This is the long part. Power. I have 165,000 horsepower. And we need to convert that. I know that 1 horsepower is 550 foot-pounds per second. I don't know how mechanical people do all this. This is just nuts, okay? You mechanicals are nuts. And I don't want to really deal with that. Feet. Okay, so I'm going to go ahead and get rid of feet. I have 12 inches per foot. So I've done my unit conversion. So I'm now in pounds and inches, at least on the top. Pounds and inches. And we may end up changing that because we're actually in KSI right here. So I'm going to just go ahead and change everything into KSI. If I have pounds, I know that if I want to go into KSI, that's a kip, and there are 1,000 pounds per kip. So we're going to go ahead and divide out on the top. So that's part of my unit conversion. And now I've got 2 pi, okay, frequency. Well, I'm told that I have this revolutions per minute. Where did that go? 36. I have 36 revolutions per minute. Okay. Well, I have seconds up here, so I need to have seconds on the bottom. And I know there are 60, there's 1 minute in 60 seconds. Okay, so I have to get rid, so the seconds need to be on the bottom. And as I'm looking at all of this, then I should be fine in terms of my units. So, sorry. And so this is what I have for my units on the bottom. Okay. And when I multiply this out, I should get 165,000 times 550 times 12 divided by 1,000, which is a big ginormous number. I'm going to divide by 2 pi. Okay. Frequency is revolutions per minute. I was thinking of angular velocity earlier, but this is revolutions per minute. So I need to divide by 36, and now I'm going to multiply by 60. And I'm left with a really, really large number, and I need to think about the units on that. So I have 288,866, okay? And if I look up here, I've got kips, so I know that's a kip, and I've got inches. Everything else canceled out. My minutes, my seconds, my horsepower, the foot, the pounds, all of that's canceled out, and this is what I'm left with for kips, is 288,866. So now we need to go back to this messy thing. So I have 25 KSI equals 288,866 kip inches. Our units are looking good. The radius outer, and then I have pi over 2, and then we have the messy part, radius outer to the 4th minus radius outer minus 12 to the 4th. Okay. And this is where sometimes you don't want to do scary math because you don't remember how to do that on your calculator. And I'm just going to start with trial and error. Sometimes that's the best place to go. Okay. And I'm just going to make some guesses, honestly. I feel like it's got to be a pretty big radius. If I have 12 inches thick, then, you know, my radius it has got to be at least 12 inches or it's solid. So we could start with, like, if we did 15 inches, that means we'd have a 3 inches out and big and thick, and that seems like kind of a right proportion. So I'm going to say, what if my outer radius is 15 inches? And when I go back and look at that, then I'm just going to go ahead and kind of simplify some of this math out. So I have 288,866, okay, pi as a number, 2 divided by, and whatever I have needs to be less than, okay, less than or equal to 25 KSI. So I want to get as close as I can to 25 KSI without going over. So I simplified this. So I'm just going to stick that in my calculator in my stack. And now when I try numbers, I just multiply it by that and see what happens. So if I have a 15, it's going to be 15 times. And then I have 15 enter to the 4th. And then I have 3 enter to the 4th minus divided by. And I get a shear stress of 54.57 KSI. And wow, that is way too high. Okay, so let's just bump it up to 20 inches. Okay, So I'm going to drop that number, and I still got my stack, which is the simplification. So I have 20 times, and then I have, 20 enter to the fourth, and 20 minus 12 is 8, enter to the fourth, minus divided by, and I get a shear stress, of 23.59 KSI. 20, that is just slightly under 25. So that's really, really close. Okay, that's really close, but I don't know if I could go up at all. So if I have a radius outer of 20, that means my diameter is 40. Okay, and it says that it needs to be to the nearest ½ inch. So let's try, what should we try? Let's try a radius outer of 19. And let's see what happens there. Okay. So if we have a 19, we're going to drop. Drop. And I'm going to take 19 times. And then I have 19 enter to the fourth. 19 minus 12 is 7. Is that right? 12, 13, 14, 15, 16, 17. Yep, 7 to the fourth minus times. And I get a really number that doesn't make sense. So I'm going to try that again. So I have 19 times, and then I have 19 to the fourth, and I have 7 to the fourth minus divided by, and I get a shear stress of 27.3, which is too high. So it says that we can have to the nearest half inch. So here we have, if we had 19, that would give us a diameter of 38. And if we have 20, we get a diameter of 40. So we could try 19.5. Okay, 19.5. See how we're doing this? We just kind of go, we can kind of go back and forth in terms of what we're doing, and see if we can get a little bit closer. Oops, where are my arguments? Well, fudgesicles. Try that again. 288866, enter pi is a number, 2 divided by. Okay, so we could try 19.5 times 19.5 enter to the fourth, so that would be 7.5 enter to the fourth minus divided by, and I get a shear stress of 25.356, which is slightly too big. Okay, that's too big. So if I have a radius of 20, that gives me a diameter of 40 and a shear stress of 23.59 KSI. If I went to a 19.5, and my diameter was then 19.5, 2 times 39, then my shear stress became too big by quite a bit more. Okay, so it says the outer diameter to the nearest ½ inch. So I guess what I could do is go 39.5, and if I have 39.5, 2 divided by, I have a radius of 19.75. And so what we can do is just try that and see. So I have 19.75 times 19.75 enter to the fourth, 19.75 enter 12 minus to the fourth minus divided by, did something wrong, 19.75 times 19.75 to the fourth, 19.75 enter, thickness 12 minus to the fourth minus divided by, and I get 24.45. So if I can go to the ½ inch, to the nearest ½ inch, if I use a radius of 19.75, that gives me a diameter of 39.5. Okay, there's my diameter, and that gives me a shear stress of 24.45. If I were to bump it up to 19.5 to 20, then I guess I went the wrong way. So I went from 20 to, now I'm all confused with what I did. So here's my 20, there's my shear stress. I bumped it down, and so I guess I should have tried a 20.5. That's what I should have done, is bumped it up. Anyways, the answer to this problem was to use a 40-inch diameter, which came from the 20. And that was the closest shear stress you got. If I tried to bump this up larger or smaller, then I had some issues. So that's how on an exam, if you don't have a way to do a solver, you just start making an educated guess. And I know it has to be less than 25. So I'm just going to start with a number that sounds reasonable with the thickness. That it's got to be like this thick. As we come around, that sounds reasonable. And then I can just come back and calculate what the stress is. And then I figured I could bump it up, and then I couldn't bump it up too much more. So anyways, that's how you do a problem like this. So the answer is use a diameter of 40 inches. I should have made a better chart.